Hey everybody, welcome to another episode of Aerospace Engineering with Brian McNulty. Today we're going to be talking about some new stuff. In the last two episodes we talked about one-dimensional motion, and then we talked about two-dimensional motion in the second episode. In those we discussed the kinematic equations, how to describe acceleration, distance, and velocity. And then we also talked about projectile motion, where we broke down motion into two components, or two-dimensional motion, and described how an object falls when it is thrown in the surface of a gravitational field. Now we're going to get to talking about forces today, and forces are an important part of physics. So if you need to go check out those previous videos to kind of understand what acceleration and velocity and position are, go for it by all means. This video will still be here when you get back. So without further ado, let's get started. Okay, so since I just said forces were an extremely important fundamental concept of motion, we should probably define what they are. So since I said forces were an important part of physics, we need to actually define what they are. Now, a force acts on an object to influence its motion or to change its direction. We can think about it in both ways like that. A force can be a push or a pull, and it requires some outside intervention. So it requires what they call an agent. And last but not least, a force is a vector, which means that it has both a magnitude and a direction. Now that we've got the general idea about what a force is, we can now talk about the different types of forces. So in this case, I'm going to talk about two different kinds of forces. I'm going to talk about contact forces, and I'm going to talk about long-range forces. So we'll start off with contact forces. Now, what you see here is an object. That fire starter log right there, that is an object. And I am going to be the agent that is imposing a force upon that object. A contact force, to be specific. You noticed as I applied that force to that fire starter log that it moved. And that was because there was an agent applying a force to the object. The force influenced the object to move. Now, some of you who have seen this before might think, okay, well, there's another contact force at play. And that contact force is friction. You notice that as I push in this direction, my push force, the friction on this fire starter log is acting in the opposite direction, resisting the motion that I am imparting onto it as the agent. There are two things that I want to make clear here. One, there is two forces in that previous example, the push force and the friction opposing it. Where does the friction come from? Well, it turns out the friction is actually the tiny little ridges in between on the glass table acting and resisting the motion of the fire starter log on top. So that was the first point I wanted to make. The second one is that the amount of force that was applied to that object goes to zero immediately when I take my finger off of the fire starter. The instant that I stopped applying force to that fire starter log, it stopped moving. Therefore, it stopped having an influence. They say that because of this, forces have no memory. So that makes sense. Forces don't remember things. So that's just something to keep in mind as we move further along into this lesson. Okay, so I'm going to give you guys a visual here. This is regarding just the two forces that I explained that were happening on this object, that were imparted by an agent, who is this little red guy here. So we have the push force, which is here on top, denoted F sub push. And then we have the force of kinetic friction, which is F sub K. And it's acting in the opposite direction. One more thing I would like you to take note of is the magnitude of these vectors. You notice that the arrow here, or the vector for push force, is larger than that of the friction force. This means that the push force overcame the friction force to be pushed to the left. Now, if the force of friction was greater than the force of the push, then we might not be able to move this object at all. But as you can see, so far we have an agent, we have a force that's pushing, and then we have the kinetic friction force in the opposite direction acting on the object. So we are going to return to that free body diagram, but before we do so, I need to explain the other types of forces, which I mentioned were called long-range forces. And these include things like gravitation and magnetism, that spooky thing that you cannot see, yet it still does have an effect on the motion of objects. And so we're going to dive into that, and we're going to see how it relates to friction, how it relates to push force, and we're going to go from there. Okay, so this might not look like much, but this is the front left tire of a car. And what this is going to demonstrate is that there is a force of gravity keeping this car on the ground. And that force of gravity is its mass times the acceleration of gravity on Earth. And so that force is going to be acting in the downward direction. However, if that's the only force occurring on it, then this car should be moving downward. So we introduce this fictitious force to make sense of all of it, called the normal force. And that just happens to be defined as a force that is acting in the opposite direction of gravity, and it is also equal to the force of gravity. So it's acting upwards. It is the force of the ground pushing up on the car. It is keeping it in a stationary vertical position. So here in our free body diagram, I have drawn these two new forces that we're being introduced to: the downward force of gravity and the upward normal force. Notice the magnitudes of those arrows. They're the same. That means that they're just going to cancel each other out, and they're not really going to have a say in how the object is moving. I said before, it just keeps the object stationary vertically. But there is one thing that it does affect, and that is the force of kinetic friction. Now we're going to take a look mathematically at how the force of friction is related to the rest of this diagram and how we're going to get the actual force of friction. Okay, so I mentioned really quickly in that last scene with the car tire that the force of gravity is just the weight, and the weight is calculated by taking an object's mass and multiplying it by the gravitational acceleration of the planet that you're on. That's why weight and mass are not the same thing, because weight is the product of the mass and the acceleration, and therefore it's a force. If you didn't know that force equals mass times acceleration, that's a good connection to make now. And I also discussed that the force of gravity has the same magnitude as the normal force. They're just in opposite directions. So that means the normal force as well just equals mg, the mass times the acceleration of gravity. Now I'm going to have to introduce a new variable here, and that is this coefficient of kinetic friction. That can be found on a table anywhere or can be experimentally determined. Typically you can just look these up on the internet, or they'll be given on your physics homework problem, so you won't have to do an experiment to figure out the coefficient of kinetic friction. One thing I do want to mention though is that mu sub k, that coefficient of kinetic friction, is always going to be a number that's between 0 and 1, and so that will kind of act as a factor to your normal force to give you the actual friction force on the object that is opposing our push force. Okay, so for the purposes of this video, I'm just going to assume that the coefficient of kinetic friction between glass and whatever material that fire starter wrapper was made out of is going to be 0.3. And I'm also going to assume that that fire starter block that we pushed at the beginning of the video weighs 3 kilograms. Now with that information, we can calculate the force of friction. let's do this. All right, so here I've just done the whole calculation. It's not that bad. We just followed the previous example. So I said that the coefficient was going to be 0.3, and that's a dimensionless quantity, by the way. That means it has no units attached to it. You notice that all the other numbers in this calculation have units attached to them. This one does not. Anyway, the force of gravity, that equals the mass times the acceleration. The acceleration in this case is going to be 9.8 meters per second squared because we're on Earth. Okay, and then this is just the mass of the object. These two, the product of these two, comprise what's called the weight. Again, don't get the mass and the weight confused. They are very different things. The weight is a force. The mass is used to calculate that force. Okay, so now that we have the force of gravity, or in other words, the weight, that's going to equal 29.4 kilograms times meters per second squared. That is actually the unit for force. And since Isaac Newton came up with the idea that the sum of the forces equals mass times acceleration, you can see you have mass times acceleration. He decided to make his own unit, and he called it newtons. So he named that unit after himself. Or I don't know if he named it, but whoever named it after Isaac Newton. And so we said that the force of gravity, the magnitude, is equal to the normal force. Since we have the force of gravity, we have the normal force. It's just the same as the force of gravity. It's the same as the weight. And we plug that into our equation here, this equation for kinetic friction that involves this coefficient and the normal force, the product of those two, and we end up with the dimensionless quantity 0.3 times the quantity with a dimension, 29.4 newtons, to give us a final answer of 8.8 newtons. Okay, so we've accounted for all the forces on the block, but I did lie when I said that was our final answer. That was simply the force of friction. But there's something called net force, and the net force is the sum of all of the forces acting on an object, and that will actually be our final answer. Now, to get that, I'll show you exactly what we need to do. Remember when I said that the force of friction acts in the opposite direction than does the force of the push? And then we also discussed that the force of gravity and the normal force cancel out, so they will have no say in this, other than determining what the friction was. But we don't need that in the final calculation for net force, because if the net force is just the sum of forces and the normal force and the gravitational force are equal and opposite, then that means that they will cancel each other out, and we're simply just left with the force of the push and the force of friction. So let's check out how to write that down mathematically. Okay, so I've redrawn our diagram here with the block, and we're going to say that this agent here, this little red guy, he imposed a push force of 12 newtons upon the 3 kilogram block. And we calculated in the previous step that the force of friction is this 8.82 in the opposite direction of the push force. We also discussed that since gravity and the normal force are equal and opposite, they cancel each other out because they're both in the vertical direction. They're just opposite of each other. So down here I've written the equation for the sum of the forces, otherwise known as the net force. And we notice something interesting happens here. This is in vector notation, by the way. This is basically the x component, or the horizontal force, and this is going to be the y component, which is going to be the vertical force. But we already said that these go to 0, and so this whole thing just cancels out there, and we're simply just left with a force in the x direction. Now, we can simply now just calculate it. We have the push force, which is 12 newtons, and then we have the kinetic friction force, which was 8.82, and so that's going to come out to be, doing this in my head here, 3.18 newtons of force. It's just the difference between it's the force of the push minus the kinetic friction force. And that makes sense because the force of the push is going to the left and the force of kinetic friction is going to the right. So they're opposite in directions, therefore you subtract. And that's going to give us the sum of the forces. And this thing, like I said before, is called the net force. So that is essentially how you are going to figure out the net force. And you're not even given the friction. I mean, we figured that all out on our own. So I think that is very cool. So I think now would be a great time to talk about Newton's 3 laws of motion. This is an important thing that he came up with in the 1600s and we've been using ever since in physics, and well, he was pretty much a genius. So we're going to follow what he says and we're going to explain these 3 laws of motion right now, and I'll talk about how they tie into our lesson today. So here we are, Newton's first law of motion. It states that an object at rest will remain at rest unless it is acted on by an outside force. In this case, that outside force was the agent and the object was the fire starter log. Okay, so to tie this into our example, you notice that before I, the agent, ever imposed a force onto the fire starter log, the object, that it wasn't moving. This works for every object in our universe. Things do not simply move on their own unless acted upon by an outside force. That is what this means. So law number 2 is going to state that the force on an object is going to be equal to the change in momentum of an object as time passes. For constant mass, the force is equal to the product of its mass and its acceleration. F equals ma. To connect this to our previous example with the fire starter log and the glass table, you can see that the object started at rest, but then it changed its velocity. By applying a force, I effectively changed that object's velocity. It went from 0 meters per second to some velocity that was not 0. That's a change in velocity. And we discussed in our previous episodes on 1 and 2 dimensional motion that a change in velocity is just simply the acceleration of an object. And so therefore we get Newton's second law, force equals the product of both mass and acceleration. So I think this one is probably the most well recited law of Newton, and sometimes I see it applied to places that it should not even be applied to, but we're going to just let that be for now, and we're just going to state, quoting Isaac Newton, for every action there is an equal and opposite reaction. In our very simple experiment that we conducted at the beginning of this video, we talked about how we pushed the fire starter log, and it wasn't necessarily apparent that gravity or the normal force were at play here. That's why I introduced the tire example. And so we can see with the tire example, the car tire, that if the force of gravity of an object on the ground is just sitting there, then there's going to be an equal and opposite force called the normal force that is acting upon that object. That makes the net force in the vertical direction 0, keeping the object from accelerating. Okay, so I've been talking a lot about acceleration, but not once in this video have I put it in any of our math calculations, and we haven't said anything about how fast the fire starter log will accelerate if I apply that force to it. So we're going to use all the parameters, the same ones that we came up with in this experiment, and we are going to determine how fast the fire starter log will accelerate under that 12 Newton push that the agent, me, gave the object. Okay, so if you guys remember from our previous calculations, we got the net force by subtracting the force of kinetic friction from the force of the push that was imposed on the object by the agent, and that happened to be 3.18 newtons. And then we determined that the mass of the object that I was pushing was 3 kilograms, but we said nothing about the acceleration, so we're going to work that out right now. And so you can see pretty simply that from this equation we can just kind of rewrite it algebraically and solve for acceleration, and that's the whole key to this entire video. Basically, you can see how fast the object is going to accelerate being pushed by a force, and so we take our net force and we divide it by the mass, and we end up getting 3.18 newtons divided by 3 kilograms. And so that is going to give us 1.06 newtons per kilogram. Now, newtons per kilogram, this unit here, is just the same thing as meters per second squared. And so that will be the acceleration of an object with constant mass given the push force of 12 newtons. And that is our final answer for acceleration. So it's absolutely worth mentioning that if I were to apply that force over a period of time, that the object would accelerate. It would not stay at constant velocity. Applying a constant force to a constant mass causes it to accelerate. It causes it to change its velocity. If this were not the case, that means that me pushing on it would have never accelerated it from 0 meters per second and the object would just stay stuck to the table. But that's not how our universe works. So to take away from this, or what to take away from this, would be that if I apply a force for a certain amount of time, during that time that I'm applying that force, the object will be changing its velocity. Alright everybody, so in this episode we talked about forces and we discussed what Isaac Newton's 3 laws of motion mean and how to mathematically represent them, and we gave an example. So if you liked the video, please like and subscribe, and I will see you all on the next episode of Aerospace Engineering with Brian McNulty. Thanks for viewing.